Bonjour de Montréal. I'm sorry I couldn't be in Paris today. I'm going to try to do this remotely. I want to tell you about challenges for deep learning towards AI. And to get started about deep learning, let me share what I consider the most important hypothesis that's behind this work and the work on neural networks in general, and the reason why I got interested into this when I started my graduate studies. So the hypothesis is that there are a few simple principles that can give rise to intelligence, whether the intelligence of machines or animals. And furthermore, that these principles are based on learning, which means that instead of describing the whole knowledge that gives us our intelligence, we only need to describe how to acquire that knowledge. And these principles hopefully would be as simple as the laws of physics, rather than the result of a huge bag of tricks and the knowledge itself. So deep learning has been making pretty amazing progress in the last decade. And I would say the area where the progress has been most impressive is perception. In other words, the ability of computers to interpret images and sometimes to convert these images into categories and sentences like you see in the example. But there's been also impressive results in the ability of computers to play games like the game of Go and to manipulate language. Something that's new is that neural nets can not only recognize images and the content of images, but also synthesize images. And a lot of that has been thanks to what we call deep generative models, such as the GANs, Generative Adversarial Networks, which we developed in my lab in 2014. And what you see here is images that were synthesized. These are not real faces. They don't correspond to any particular person. And we see the progression of the quality of these images over the years. Another big breakthrough to which my group participated is the use of what's called content-based soft attention. These attention mechanisms use gating units which can control the flow of computation. And we use this in machine translation to build machine translation systems which eventually were adopted by Google in Google Translate in 2016 and have made it possible to make a big jump in the quality of translations from the original classical systems based on n-grams to the current neural machine translation. Now, in spite of all this progress, I think we have to be really careful and downplay the hype that sometimes is heard, because we are still very far from human-level AI. First of all, the kind of industrial success that you can find out there in your phone or in many other applications on the internet are based on supervised learning, meaning that it has been necessary for humans to provide a lot of high-level labels, high-level categories that help the computer figure out the sort of abstractions that we wanted to recognize. And then when we look at the kind of mistakes that these systems make, we realize that they don't really understand images or sentences. They seem to rely on fairly superficial clues that don't allow it to generalize well outside of the training context. So for example, the images you see on the right are recognized in one case as dog on the left, and then if you tweak the pixels in a way that you don't perceive, but that makes a big difference in the output, the network says it's an ostrich. I think it's interesting to maybe put in perspective where the current deep learning systems are strong and where they are weak. And roughly speaking, so I was talking about perception, but more generally, this is the kind of tasks that psychologists call system one tasks. These tasks are intuitive, they're fast, often they use heuristics to solve the problem, and they're unconscious. We don't have conscious access to how we solve these problems. And so it's hard for them to explain how we solve those tasks. They're not really linguistic, which also explains why it's difficult to interpret what those systems are doing. Now, there are lots of useful tasks that can be addressed using this sort of ability, but humans are also able to perform a different kind of task called system two. For example, if I ask you to add two long numbers, The way you're going to be doing this is very sequential and slow, using logic, and you're going to be conscious of what you're doing in every step of the way, and you can talk about it. This is the kind of ability we use when we design an algorithm or we try to understand an algorithm, for example. And this is also what classical symbolic AI was trying to do and failed for a number of reasons, such as not capturing uncertainty properly and not being grounded in the underlying sensory perceptions, which is what current deep learning does well. So really we'd like to bring these two types of abilities together. And the gist of my message this morning is that one of the important ingredients to do that is to consider what's called grounded language learning, in which we learn about language as well as about a world model that captures the sort of intuitive knowledge and common sense knowledge of the world that System 1 tasks are relevant for. To illustrate the limitations of current systems, it's interesting to look at their performance on what's called the Winograd schemas. So these are sentences that have a semantic ambiguity. For example, the women stopped taking pills because they were pregnant. And then we want to know what they refers to. Is they the women or the pills? If we change pregnant to carcinogenic, it changes the answer. Humans are very good at these kinds of tasks. In fact, they're essentially 100% accurate if you think about it. But current machine learning systems can only do barely better than chance. So if we try to understand how is it that our current systems don't manage to solve these problems, one important question that comes up is the kind of knowledge that humans seem to use in order to figure out the answers. And it looks like a lot of that knowledge we acquire as humans in an unsupervised, fairly autonomous way. For example, a 2-year-old child has learned about intuitive physics, things like gravity and forces and pressure and solid objects and liquid objects. All of that, the parents of the child don't need to teach her these concepts. She just observes the world, interacts with it, and manages to figure out some very important intuitive properties of the world. So this is true of intuitive physics, where we have good formal knowledge to describe the world, but it's also true of intuitive psychology, where children learn about how to relate to each other and to adults. And for that, we don't have as clearly defined formal knowledge, of course. But in both cases, our current systems are not that great at exploiting that sort of underlying knowledge. And I'm going to argue that in part is because that kind of knowledge isn't available in text, in natural language. So I think the big question when we're doing AI is where is the knowledge that is necessary to solve the task? If we really want a machine to understand a question, understand a document, that machine will need to have the appropriate knowledge to make sense of that document. And then from a machine learning point of view, the question is, how are we going to get that knowledge into the computer, and where are we going to get that knowledge from? So in order to see the limitations of working purely with text, as we have been doing for decades in machine learning and AI, I'm going to propose that you consider this thought experiment, which is going to illustrate one of the limitations of working only with text in order to build systems which understand our world. So imagine you approach a planet that has aliens, and you're trying to make sense of their language. And from your spacecraft, you're able to capture the bits that they're exchanging when they talk to each other. But on that planet, let's say that things are a bit different from Earth, in the sense that the aliens are able to communicate with each other with a noise-free channel, meaning that they can compress their signal as much as possible. Whereas on Earth, we have a noisy channel, like speech is noisy, and so there's a lot of redundancy in human languages. So both on Earth and on this planet, we try to reduce the number of bits that we need to exchange because there is a price and time to exchange information if we don't compress it. And so what's going to happen on this planet is that the aliens have found a way to really do a good job of compressing the message they want to exchange. The bad news is that the compressed messages look just like noise. They are just going to be a sequence of random bits that seem to be having nothing to do with each other. And so if we do language modeling as we traditionally do it in machine learning, by modeling the joint distribution of words, then we'll never be able to understand anything about that language. So how could we solve the problem if we are on this planet? Well, the solution is obvious, but it's not going to be easy to implement. We want to do grounded language learning. So that means that in addition to bits that the aliens exchange, we need to observe what they're doing and trying to figure out their intentions and the message that they're trying to communicate based on the context. Obviously, this is going to be difficult. It's going to take a lot of work. We have now to build, in addition to a language model, an alien world model, which captures the causal structure of their behavior and how that is associated with their communications. So one problem, as I said, with current natural language processing is that it's mostly based on training on large quantities of text. So for example, the machine translation systems I mentioned to you are trained by text, pairs of a source document and a target document in another language. And that's the data from which the systems are trained. And based on two problems that I've talked about. So one is that language may be incomplete in the sense that there may be information about the meaning that is absent from the text itself. And two, the fact that we know that humans don't communicate everything by language. There's a lot of intuitive knowledge which doesn't get communicated because we don't have conscious access. The result is that we're going to be missing some knowledge about the world that's going to be necessary to make sense of it and really understand those sentences. And in particular, if we want to have systems that can capture the causal structure of the world and reason about it, because that's what you need in order to do proper reasoning, we really need to build good models of the world. At this point, it's interesting to think about how researchers could make progress towards building good world models, because the world around us is very, very complex, and it seems a very daunting task. And in fact, as I'll tell you later, the current techniques that we have are not doing a very good job of making sense of the world around us. So what would allow us to speed up the research cycle is to work with virtual environments where the experiments can be done much faster than, say, working with robots. And then as we make progress in solving those environments in the sense of having systems that can really understand them fully, we can design gradually more complex environments. And the reason why this strategy works, we're not actually trying with machine learning, we're not actually trying to build the full knowledge of the world. The actual result of the research are learning procedures. And those learning procedures are supposed to be very general. They should work on many different kind of environments, ultimately in our real world environment. So we can test these learning procedures and their weaknesses on these virtual environments in order to find their limitations and then solve those problems. So in my group, we've started working on a project which we call Baby AI, or the Baby AI game, which is precisely in this direction of building a virtual environment in which we're going to associate actions and perceptions in some environment with natural language. So we have built this series of levels in this grid world. The agent that is supposed to do things in this environment only sees part of the environment. This is a very important property. This is called partially observable. And it's given instructions about things to do, about objects, about locations and actions, such as go to the red ball, open the door on your left, or something more complex like put a ball next to a purple door after you put a blue box next to a gray box, and so on. So let me tell you a little bit about of the experiments that we have run on this benchmark, which is actually now available online. And you can also find a description of this in an ICLR submission online, if you type baby AI ICLR. The results of the experiments we've run is that the current state-of-the-art methods for reinforcement learning and imitation learning are actually far insufficient to solve even these fairly simple environments. Insufficient in the sense that the number of samples, the number of examples that the learner needs to look at in order to solve these tasks is just way too high. It's it's going to be in hundreds of thousands or millions of trajectories that it needs to see. And if we want the feedback that is going to be used to train those agents to come from humans, because eventually in natural language, we won't be able to program these kind of pseudo language that I've been telling you about. It's going to have to be interactions with humans. But a human is not going to be willing to spend millions of minutes or a large time with an agent in order to train it to understand its environment. So in a sense, the good news is it means that even in those simple environments, there is interesting research to be done, and we don't even need to consider very, very complex environments. We have tried to use some of the techniques of curriculum learning, for example, in order to improve things, in the sense that as I say, we have defined a set of tasks that are gradually more difficult. And curriculum learning is about initially training on easier tasks and then gradually asking the learner to solve more complex tasks. And in many instances in the past in machine learning papers, we find cases where this technique helps. In our experiments, it does help, but not as much as we were hoping. So maybe it can divide by 2 the number of samples needed, but this is far insufficient compared to our objective. If we consider some of these tasks, a human which would master some of the building blocks, like understanding how to find an object in one room and how to navigate in a large number of rooms, would be able to solve the more complex task of finding an object in a large number of rooms with just a few examples, whereas those systems still require hundreds of thousands of examples. All right, so let me try to summarize the message that I've been trying to put forward today. We have made a lot of progress in supervised learning, but humans are able to learn in a more autonomous way. And even though there's been a lot of research in unsupervised learning, I think we are far from having solved this ability at the level of human. And it's going to be important to really complete our progress in System 1 tasks. But in order to really go further, we need to handle the problem of quality, something that researchers are starting to handle in machine learning, but right now we are only making baby steps with that. Second, we need to consider learning from texts, but also from environments, including the concepts that the text refers to. And the I gave for this are that there's knowledge about the environment which is necessary in order to really understand a sentence, but that is not given in text, that it is something that we as humans figure out by being in our environment and trying things out and observing how the world works. So another aspect that is important which I haven't really taken time to talk about, that's relevant to unsupervised learning is how we do unsupervised learning for agents, right? So most classical unsupervised learning has been with passive observation of, say, images. But in the context where you want to learn about causality, you want to learn about the cause and effect, you want agents that intervene in the environment. And so now we want to think about a different kind of unsupervised learning concerns agents which can actively seek information in their environment. So this is another area which I think requires a lot more work. Another direction to, I think, address as we are building these world models is that the current type of world models that we are considering in machine learning don't look at all like the world models that humans have in their head. So we don't plan or we don't visualize the whole future one time step after the other with the full state of the world at each time step. Instead, when we imagine the future and we plan, we are only considering a few key events in the future and a few aspects of the world at a time. So basically, to put it together, I think we need to expand and lift the current deep learning systems that are really good at System 1 cognition to the sort of high-level reasoning and semantic modeling of the world that is characteristic of System 2 cognition and human intelligence. Thank you very much. Merci beaucoup.